Hello students, in today's video we're going to be working on definite integrals and antiderivatives. So let's get started. Go ahead and take a second to copy this table in front of you. I'm going to go ahead and enlarge it. It's not enlarging. Let me make this bigger for you guys to see. Go ahead and pause your screen and write everything on this table down, please. So hopefully you've paused your screen and wrote that down. We're going to look at these rules for definite integrals one by one. So let's look at this one. So what I want you to look at first is notice on the left hand side we have the definite integral. That's this sign right here. What makes it a definite integral is that we have this lower limit a and this upper limit b for the function f of x dx. What you'll notice in the second part is that they threw a negative in front. What that does is, in order for us to keep that equality, for these two things to be equal, if you throw a negative in front, you can reverse your upper and lower limits for these integrals, and the rest will stay the same. So that's going to help us a little bit later on when we do these example problems, but I wanted you to get a look at them now. Let's take a look at another property. Notice here when you have the same upper limit and lower limit, that integral is always going to be equal to 0. And the reason why is because you're integrating over the same part. So imagine finding the integral or the area under a curve like we have in the past few days where you're looking at a geometric shape. Well, if you're going from A to A, you're really not moving at all, which means you're not going to have any width, which means you couldn't possibly have any area. Let's look at another one. So here's another one that's really important to notice. Notice here that we have the integral from A to B of k, where k is a constant, times f of x dx. And what we could do with these is pull out that constant in front, and you can still take the same integral and multiply the constant at the end. This will make this a lot easier. For example, if k were equal to -1, notice how the k in this particular instance is after the integral. We moved it to the front and it's exactly the same. So that's the same thing as us pulling just our constants to the front of any function. Let's look at number 4. Number 4, we're looking at the integral from a to b for f of x plus or minus g of x dx. All that means is we can take each function f of x and g of x and separate them over the same integral limits, and we would still end up with the same values. This way it's a lot easier for us to break down and take a look at individual functions. Number 5, we have the limit from a to b of f of x dx plus the limit of bc for f of x dx is equal to the limit from a to c for f of x dx. So notice here at our definite integrals, we have an integral that starts from a and goes all the way up to b and then continues from b to c. So what we've done here is we can rewrite that integral as 1 and say it goes from a through b and finishes at c, and we would get the same exact integral, or the same exact value. Let's look at 2 more. So here's the first. We are saying that if we have some integral from a to b for f of x dx, we're saying that's going to be less than or equal to the max of f times the difference in our limits. And we're saying that function is going to be greater than the minimum of f times the difference in their limits. So it's basically just saying in between this function we have a max and a min. Looking at 7. Here we say that we have a function f of x that's greater than or equal to g of x for every value on the closed interval a to b. So if that's the case where f of x is always greater than g of x on that closed interval from a to b, then it's saying that the integral from a to b for f of x is greater than that of g of x. So imagine if we took a line like so, and we split that up down the middle, right down here. And if we called this g of x, and we called this f of x, if we were supposed to find the area under the line, or under the curve, the area of g of x would be less than the area of f of x all the time because f was always greater. So let's look at a couple practice problems. So let's take a look at letter A. A is saying we have the integral from 1 to 9, and we have this function negative 2 f of x. So notice right off the bat, we could pull the negative 2 up front, and then we'll have that integral from 1 to 9 for f of x. Now if you take a look, we have the same exact thing here. And it's saying from 1 to 9 for f of x dx, that's equal to negative 1. So here we have negative 1. So negative 2 times negative 1 is equal to 2. And now we have that answer for that particular problem. Let's look at the next portion. Notice here it says the limit from 7 to 9 for f of x plus h of x. So if we have the limit from 7 to 9 of f of x, that would just be 5. And the limit from 7 to 9 for h of x is 4. So in example B, all we're saying here is that we have 5 plus 4. Because if you line it up, f of x is 5 and h of x is 4. Let's take a look at letter C. C has the same integral here, 7 to 9, for 2 times f of x minus 3 times h of x. So we basically have 2 times the integral of f of x minus 3 times the integral of h of x. So that would be 2 times that f of x from 7 to 9 is 5 minus 3 times 4. So that's going to be equal to our negative 2. So I hope this is turning out to be pretty easy when you take a look at it. Let's look at another example. Here, notice that our lower limit is 9 and our upper limit is 1. First of all, we never want to have that because your smaller number should always be on the lower limit. And so what we're going to do here is we're going to use the negative sign to flip it. So if I throw a negative sign in front, this integral changes. Now it becomes 9 to 1 for f of x. And we know that we have the negative times f of x from 1 to 9 is negative 1. So your answer here is just 1. And if we take a look at part E, notice E is a little bit different. It says it goes from 1 to 7. Now for these limits, we don't have anything up here that goes from 1 to 7. However, we do know we have a limit that goes from 9 to 1. And if we subtracted, actually, from 9 to 7, that would give us our answer of the integral from 7 to 1. So let me go a little bit further, just in case it didn't make sense. Here in this limit, we're going from 1 to 9. That's going to be a fairly larger area. So pretend we have, it looks like a triangle, because I know we talked about this a lot. It goes from 1 to 9. Now they just wanted to go from 7 to 9, so just from here to here. Problem is, when we did 1 to 9, they gave us an entire triangle here. So we want that whole triangle minus this part. And so that part is from 1 to 7. So, I'm sorry, we want the 1 to 7. We need to get rid of this 7 to 9. So, we know the limit from 1 to 9 is negative 1. And then notice we have the subtraction sign here. We know from 9 to 7 it's 5. Then we know that our answer here is going to be negative 6. So, next thing is, give me a second. And finally, let's look at the last one. So if we look at f, we know that it's going from 7 to 9. So we don't like that one because remember, we have our limits going from 9 to 7. The bigger number, the larger number is going to be on the top. So what we're going to do here is we're going to take our h of x and make that a negative so we could flip that integral. And then we already have a negative on the f of x. We're going to have a negative f of x. So negative integral of f of x. And what that's going to do, we're going to have a negative here, and the integral of h of x from 7 to 9 is 4. We know that these two addition signs down here are going to become a positive, and we know that the integral from 7 to 9 for f of x is 5. Therefore, our answer is just going to be 1. So now you found the limits given the rest of those functions. So let's take a look at a couple other things. The average value of function. And this basically says that if f is integrable on the closed interval a to b, its average value, also called the mean value on ab, is given by this function below, or this formula below. So we'll go ahead and write that down. What we want to do is look at that in practice. So here we're going to find the average value of y equals the quantity x minus 1 squared on the interval 0 to 3. And then at what point or points in that interval does the function assume its average value? So based on the formula that we were given on the last page, is basically 1 divided by b minus a times the integral of x minus 1 quantity squared from 0 to 3. So we're looking at here, when you see this integral, we're saying that integral from 0 to 3. This is when you're going to want to punch this into your calculator and tell us the integral of this function from 0 to 3. We know when we do this left side portion, it's going to be 1 divided by 3 minus 0 times, and then if you did this in your calculator, like you're supposed to, you will get the answer of 9/3, which obviously is 3. So then you're going to be left with 1/3 times 3, which is equal to 1. The next portion of the question says, at which point or points does the interval assume its average value? So all they're saying in this second part, that when does this function hit that average value? Well, what they're saying here is we have this function, y equals x minus 1 squared. So when is that going to be equal to 1? So we're going to go ahead and do here is square root both sides. And what you're going to be left with is plus or minus 1. And we're left with plus or minus 1 equals x minus 1. Then you're going to add 1 to both sides. You're going to be left with x equals 1 plus or minus 1. means you're left with x equals 2 and 0. And notice that because 0 and 2 are both in that closed interval 0 and 3, this is going to be the points where it hits that average value. So, what I'd like to do is move a little bit more ahead. And I'm going to ask you to find the antiderivative of this function. So here's what we're going to do. This is kind of like doing the chain rule. And I know we worked on derivatives or antiderivatives a little bit. So we're going to start in the following fashion. I know that you can do the basics of this for now. So what we're going to do is I'm going to let u be equal to 3x minus 5. And then what we're going to do is we're going to find du. Du is going to be equal to 3 dx. And the reason why we're doing this is because it's going to make finding this integral much simpler. Because what we're going to end up doing is instead of having 3x minus 5, we have u to the second power. Now we mentioned this a little bit. When we're trying to find an antiderivative, we're finding the opposite of a regular derivative. So we're going backwards. So if we were trying to find the derivative of u squared, actually before we move on, we had dx in here. So what we're going to do is dx, according to our work here, dx would be equal to du divided by 3, or du times 1/3. And since we took out the 3x minus 5, we also have to take out the dx. We know that dx is equal to du times 1/3. So now let's go back to the integral. If we were to find the derivative of this, we would do chain rule or power rule, where we move the 2 forward. We take the 2 here, and we'd subtract 1 from here. That would be finding the derivative. So the opposite of subtracting 1 to both sides and moving the 2 to the front as a multiplication is to actually add 1. So what's going to end up happening is we're going to now do u to the second power plus 1 instead of subtract 1. And then instead of multiplying by 3, we're going to divide by 3. And we're going to be left with u to the third power divided by 3. And you'll notice we had this 1/3 hanging out right here. So we have to continue that and put that here. So we're going to be left with another 1/3. And if we simplify this further, we're going to be left with 1/9 u cubed as our final answer. Oh, not as our final answer. That's our integral. But remember, we have to put that x value back in. So 1/9 times 3x minus 5 to the third power. And this is your final answer. That's the antiderivative of 3x minus 5 quantity squared. So the other thing I wanted us to look at is evaluating different definite integrals. Remember, a definite integral means they give us actual limits here. They give us values. In this particular case, it's a to b. And so what happens when we evaluate definite integrals is first we take this little f of x dx and we find the antiderivative. When we find the antiderivative of little f, it becomes big F. And then we substitute our upper limit b, which is here, and we subtract that from our lower limit a, which is right here. And then that answer is going to be the answer to our definite integral. So let's try a couple together. So we have 2t minus 3. And when we take the antiderivative of this, what we're going to be left with is 2t squared divided by 2. Because remember, instead of multiplying, we're going to divide. And then we're left with minus 3t. And what we do with definite integrals is we write them up like so, have that little vertical line, and then we write 2 up at the top here, and 0 down here. And from there, we're taking our equation. Also, I'm going to take this 2 divided by 2 and simplify that so it's easier for us. So basically, you have t squared minus 3t, and we're substituting. So we're going to substitute that t with a 2. So we're going to have 2 squared minus 3 times 2 minus 0 squared minus 3 times 0. And so we're going to be left with 4 minus 6 minus 0. And so our final answer here is going to be negative 2. So let's look at another example. Number 4, we have the following function. We have 3x squared plus x minus 4. So when we find the antiderivative of this, we're going to have 3x cubed, remember we're adding 1, divided by 3. And plus x squared divided by 2 minus 4x from 4 to 2. And then we're going to substitute everything in. So again, we're going to simplify this 3/3 and just make that x cubed. And now we're left with 4 cubed plus 4 squared divided by 2 minus 4 times 2. Oh, minus 4 times 4, my apologies. And that's simplifying just the 4. Remember, we have to subtract that from our lower limit. So our lower limit is going to include the 2. So it's going to be 2 cubed plus 2 squared divided by 2 minus 4 times 2. And when you plug this into your calculator, or not when you plug into your calculator, when you work this out, it turns out to be 54. So do yourself a favor. Look at how I separated this and this with a subtraction sign and multiple parentheses. This left hand side is going to turn out to be 56 minus 2, and that's how we're going to get our negative 54. So that's all for now. We'll do more practice of this in class, and so that's all for now. I'll see you guys next time.